Welcome to Mathematics 1. My name is Neil Koss. I'm going to start by giving some information about this course, and then we'll have our first lecture. I'm expecting to give you approximately 12 classes. They'll be on Friday afternoons between 2 and 4:30. If you check your calendar, you'll see we might have time for 13 classes, but usually something comes up and we lose at least one class each term. So my plan is to do 12 classes and then we'll adjust as necessary. What I'm going to do is I'm going to give you 2 lectures with a break in between, and then after that I'll be available to answer your questions. This course is based on the book Thomas's Calculus by Haas, Hale and Weir. This is a required purchase. You need to buy this book to be able to do the homework. We offer 4 mathematics courses to engineering students. Mathematics 1, 2, 3 and 4. This is Mathematics 1. Mathematics 1 and Mathematics 2 use the same book. They cover topics from calculus. Mathematics 3 is about a different type of mathematics. That's about linear algebra. And then Mathematics 4 brings the ideas of calculus and linear algebra together to study differential equations. In this course, we're going to cover the first 7 chapters of the textbook. So we'll start by talking about functions, and then limits and continuity, derivatives and applications of derivatives, integrals and applications of integrals, and then in the final 2 weeks, transcendental functions. And my plan is finish talking about functions today. Then that will give us 2 weeks to talk about limits and continuity, 4 weeks in total to talk about derivatives and applications of derivatives, 3 weeks to talk about integrals and applications of integrals, and then the final 2 weeks will be about transcendental functions. This course is examined with exams and homework. The homework, which is worth 20% of your mark, will be using the book publisher's website, using the MyLab Math website. There will be 12 pieces of homework and they will align roughly with the lectures. The course ID is in OLearn. Click on the homework and you'll find it, but you shouldn't be asked for that. The deadline for all of the homework will be after the end of term. It will be 1 day before the final exam. So you have time to work on the homework at your own speed, but I would recommend you try to do 1 each week. If you click on homework on the left, you'll see there's 3 links: MyLab Math course, MyLab Math homework, MyLab Math gradebook. Click on any one of these and you'll go to the registration of the MyLab website. You shouldn't need to enter the course code, but if you do need it, it's here in the 4th entry on this page. Let me check that after the lecture's finished. There should be 4 homeworks available at the moment. I've only written the first 4. The last 8 I haven't written yet. There will be 2 midterm exams for this course. The course ID is in Okan. Click on homework and you'll see it in the 4th entry. The midterm exams will be face-to-face exams. I'll announce more information about them near the time. And the final exam will be worth 40%. That will also be a face-to-face exam. If this was a classroom course, then you would be given 5 hours of lectures every week. And the expectation is that you would study another 1 or 2 hours outside of class for each one of these 5 hours. So that makes this a 10 to 15 hours every week. For an online course, it's still considered to be 10 to 15 hours each week. But because we only have 2.5 hours in class, that means you're expected to do some more studying by yourself. What could that be? Well, there's the online homeworks on MyLab. You can rewatch the recorded lectures. I'm going to make them available both on OLearn and on YouTube. I'm making all of my lecture slides available to you. Read them before the lecture, read them after the lecture, up to you. Of course, you should be reading the textbook. I'm trying to pick out the key points, but the textbook has more details and more examples than I will be covering. The textbook has lots and lots of nice exercises in. You should be trying to solve as many of these as you can. Some of them have answers in the back of the book. In OLearn, there's a discussion board. I'm checking this almost every day. If you want to ask questions, if you want help understanding the material or with homework questions, you can ask there. If you see another student asking and you know the answer, then please feel free to explain how to solve a problem to them. Perhaps you would like to read some other books about calculus, or perhaps you want to watch some videos by other lecturers. Yes, this is recorded. If you look at the bottom left of my slides, you'll see the slide number. This will tell you roughly how far I am through a lecture. And if you're following along on the textbook, I've written the section number and title at the top. The recording will be in OLearn and on YouTube. Let me share my screen again. If we click on Colab Classroom in the left menu, we get to this normal screen where we join the lecture. Find the hamburger menu, the 3 horizontal lines, click this, and then there's an option for recordings. And at the moment, this is empty because we haven't finished our lecture. About 10 minutes or 15 minutes after we finish, you'll find today's recording here. That's the end of the information about this course. Yes, you need to buy the book. You'll find information about that in OLearn. Check the announcements. I'm going to start by talking about real numbers and the real line. This is one of the appendices at the back of your textbook. And then I'm going to spend the rest of the lesson talking about functions. Functions and their graphs, combining functions, shifting and scaling graphs, and trigonometric functions. The first numbers that children learn are the counting numbers, the numbers 1, 2, 3, 4, 5, and 6, etc. These are called the natural numbers. The set of these numbers is written with this hollow capital N. So for example, 2 is a natural number. 2 and then this type of E and then N means 2 is a natural number. 7 is a natural number, but a half is not a natural number. For the fourth one, there's some disagreement, but most people in the world agree that 0 is not a natural number, and negative numbers such as -5 are not natural numbers. In the natural numbers, we can do two operations. We can do addition and we can do multiplication, by which I mean if we add two natural numbers together, we still have a natural number. If we multiply two natural numbers together, then we still have a natural number. But we can't do subtraction in the natural numbers because sometimes we get a number which is not a natural number. For example, 2 minus 7 is not a natural number. So what do? What did humans do in our history when we first encountered this problem? So we invent new numbers. Next type of numbers that humans thought about were the integers. The set of integers is written as this hollow capital Z. That's all the natural numbers and 0 and all the negative of the natural numbers. In the integers, we can do addition, subtraction, and multiplication, but we can't do division. For example, 3 plus 4 is an integer, 3 minus 4 is an integer, 3 multiplied by 4 is an integer, but 3 divided by 4 is not an integer. So what do? What did humans do in our history? So we invent new numbers. The next numbers that humans invented were the rational numbers, or the fractions. Let this hollow Q be the set of all fractions. And to be more precise, I mean all of the numbers which are of the form a divided by b, where a and b are integers and b is not equal to 0. For example, 0 is a rational number, 1 is a rational number, 3 over 4 is a rational number, but pi is not a rational number. 100 over 13 is a rational number, but square root of 2 is not a rational number, etc. In the rational numbers in Q, we can do addition, subtraction, multiplication, and division, as long as we're divided by a number which is not 0. So are we happy now? Do we have enough numbers to be able to do calculus? And the answer is no. Why are we not happy? Because if we try to draw a picture of the rational numbers in a line, then we're going to be drawing a line which has lots of holes in it. In fact, the rational numbers has infinitely many holes in it. So what do? What did humans do in our problem? What did humans do in our history once we realized this problem? So we invent new numbers. And the numbers that we invent, the numbers that humans invented in our history, is the real numbers. We denote this by this hollow capital R. That's all the numbers which can be written as a decimal. For example, 0 is a real number, 23 over 99 is a real number, 3/4 is a real number, pi is a real number, etc. The real numbers are complete. That's a fancy way of saying that if we draw the real numbers in a line, then there's no holes in the line. So are we happy now? In other words, do we have enough numbers to be able to do calculus? And the answer is yes. Now we can do calculus. We're going to need things called intervals in this course. A subset of the real numbers is called an interval if it satisfies these two rules. First, the subset needs to contain at least two numbers, and rule number two, the subset doesn't have any holes in it. So for example, the set of x such that, this vertical line means such that, x is a real number and x is strictly greater than 6. This is an interval. There's at least two numbers here, because, for example, 7 and 8 are both in the set, and there's no holes inside this set. Let me just remark before we go on, the end point of this interval, which is 6, is not in the set because 6 is not strictly greater than 6. Just to show this in a picture, we can draw an open circle at 6. Next example, the set of all real numbers x such that x is between -2 and 5 is an interval. There's at least two numbers in this subset, and there's no holes in the middle. The end points of this interval are contained inside the set. If I want to show this in a picture, I can draw a filled-in circle at -2 and at 5. The set of x such that x is a real number and x is not equal to 0 is not an interval. Why? Because it has a hole in it. It has a hole at 0. We can classify intervals as either finite or infinite. A finite interval can then be further subclassified as either closed, half open, or open. We say it's closed if it contains both of its endpoints, half open if it contains only one of its endpoints, and open if it does not contain its endpoints. So for example, let's look at these four. The first set is a set of real numbers x such that x is between a and b with strictly less than symbols. And I've drawn a picture of this on the right. This is an open interval because the endpoints are not in this subset. We denote this with round brackets. Round bracket a, comma b, round brackets. The second one, which we denote with square brackets, is a closed interval. It's closed because the endpoints a and b are both in this set. And the bottom two, these are half open intervals. They're half open because one of the endpoints is in the set and the other one is not in the set. If the endpoint is in the set, we use a square bracket. If the endpoint is not in the set, we use a rounded bracket. An infinite interval can be either closed or open. It's closed if it contains a finite endpoint, and it's open if it's not closed. There's one exception to this rule. If we have the whole real line, which is an interval, then we say that that's both open and closed. And that's so that some higher mathematics, some topology is consistent, so that it works when we get to more difficult maths. Here are 5 different types of infinite interval. The first one is an open interval. It's round bracketed a, comma b, sorry, comma infinity, round bracket. That's all of the numbers x which are strictly greater than a. That's an open infinite interval. Change the round bracket at a to a square bracket. We have a closed interval from a to infinity. We could do the same going to the left instead of going to the right. Minus infinity, comma b round bracket, or minus infinity, comma b square bracket are open or closed. And then finally, the interval from minus infinity to infinity, we write that as round bracket, minus infinity, comma infinity, round bracket. That's all of the real numbers, and that's both open and closed. Sometimes we might want to combine two or more intervals together. We can do that with the union notation. For example, I've drawn a picture here of the closed interval from -8 to -2, union the closed interval from 2 to 8. This is not an interval itself because it's got a hole in the middle, but it is a union of two intervals. Okay, that's enough about numbers and intervals. Now we're ready to start chapter 1, to start talking about functions and their graphs. We're going to be writing things like this. Y is equal to f of x. Here, f is going to be our function, x will be our independent variable, and y will be our dependent variable. X will be any number that we want to put into the function, and then y will depend on x and f. Strictly speaking, what is a function? A function from a set D to a set Y is a rule which assigns a unique element of Y to each element of D. The set D of all the possible values of X is called the domain of F, and the set Y is called the target of F. The set of all possible values of f of x is called the range of f. If we have a function with domain D and target Y, we can write it like this. F colon D arrow Y. This is a function which goes from D to Y. So, for example, a function f which maps from the real numbers to the real numbers and has the formula f of x is equal to x squared. A different function is a function f from the interval from minus infinity to infinity. That's the same as the real numbers, so no change so far. And it has the same formula, x squared, but it has a different target. Now the target is just the positive real numbers or the non-negative real numbers. So that makes it a different function. We can think of functions like this. We have our domain, and we have our D, and we have our target Y. We can think of a function as a collection of arrows from D to Y. And then after we've done that, we can ask, what are the values in Y which have an arrow pointing at them? Not every point or not every number in Y will have an arrow which points to it. If we just count the ones which have an arrow pointing to it, that's called the range of F. We might also like to think of a function as some sort of machine where we put a number into the machine and we get a different number out of the machine. Sometimes we're going to want to use the largest possible domain for a function. This is called the natural domain of the function. And sometimes we're going to want to use a smaller domain. Let's look at some examples of functions and their domains and their ranges. For the first function, my function is y is equal to x squared, and I want to use the domain minus infinity to infinity. What possible values could y take? If x is 0, then y is 0. If x is 1, then y is 1. If x is 2, then y is 4, and so on. You can get bigger and bigger and bigger above 0. If x is minus 1, then y is 1. If x is minus 2, then y is 4, and so on. We can get to any number between 0 and infinity, but we can't make y be a negative number. So the range of this function is going to be the closed interval from 0 to infinity. Second function, y is equal to 1 over x. The natural domain of this function, that's the biggest possible domain of this function, is all of the real numbers except x equal to 0, because we can't divide by 0. What's the range of this function? Well, if x is 1, then y is 1. So 1 must be in the range. If x is 2, then y is a half. We know that a half must be in the range, and so on. If x is 10, if x is 1,000, if x is 1,000,000, we can calculate y. And we can see we can get smaller and smaller, closer to 0, but not actually equal to 0. If x is a half, y is 2. If x is 1 over 1,000, then y is 1,000, and so on. We can get bigger and bigger if we wanted to. If x is a negative number, we have the same thing. We can go all of the way to minus infinity, and we can get close to 0. The range is the same set. It's all of the numbers y which are in the real numbers but are not equal to 0. Third function. We can't take the square root of a negative number if we're working in the real numbers, so our natural domain of the square root function is going to be the closed interval from 0 to infinity. What would the range of this function be? Well, we can do some examples. We can look at square root of 0, square root of 1, square root of 4, etc., and keep going bigger and bigger. Square root of 1,000,000 we could look at. All of these numbers must be in the range. The range must be the same set. We can't make a negative number using the square root function, but we could make any positive number that we wanted to. Y is equal to the square root of 4 minus x. I could put x equal to 4 in it, that would be okay, but I can't put x equal to 4.1. Then we would end up taking the square root of a negative number. So the natural domain, the biggest possible domain, would be the closed interval from minus infinity to 4. What would the range of this function be? We can think of a few examples. If x is 4, then y is going to be the square root of 4 minus 4, square root of 0 is 0. So 0 must be in the range. If x is 3, if x is 2, if x is 1, what's happening? If x is 3, then y is the square root of 4 minus 3, square root of 1 is 1. If x is 2, y must be the square root of 4 minus 2, that's the square root of 2, and so on. It keeps getting bigger and bigger. The range of this function must again be the closed interval between 0 and infinity. The square root of 1 minus x squared. X needs to be between minus 1 and 1 for this to make sense. What is the range? I think we just need to look at 3 numbers here. Just think about minus 1, 0, and 1. If x is minus 1, I have square root of 1 minus 1, or 0. if x is 0, square root of 1 minus 0, that's 1. And if x is 1, again, we have square root of 0. It looks like we're going to have all of the numbers between 0 and 1. And in fact, yes, that is the range of this function. Three more functions, y is equal to x squared, y is equal to x squared, y is equal to x squared, but this time with 3 different domains. If the domain is the closed interval between 1 and 2, what is the range? Which values could y take? Right. If x is 1, then y is 1. If x is 2, then y is 4. If x is between 1 and 2, then y should be between 1 and 4. The range is the closed interval from 1 to 4. What about if we say the domain is the closed interval from 2 to infinity? Then the range is going to be the closed interval from 4 to infinity. How about if the range is, so how about if the domain is the closed interval from minus infinity to minus 2? Well, if we choose the endpoint, x is minus 2, again we get y is equal to 4. If x is minus 3, we get y is equal to 9. If x is minus 4, we get y is equal to 16. We're getting bigger and bigger and bigger again. So again, the range is the closed interval from 4 to infinity. And the final two, if y is 1 plus x squared, and x is between 1 and 3, then y must be between 2 and 10. If y is 1 minus the square root of x, and x is a non-negative number, then y must be between minus infinity and 1. I want to talk about graphs of functions. Formally, the graph of a function f is the set containing all of the points x, y, which satisfy the equation y is equal to f of x. And you might be asked to draw the graph of a function, or graph the function y is equal to 1 plus x squared over the interval from minus 2 to 2. The first thing I'm going to want to do is I'm going to want to make a table of x, y points which satisfy this equation. And I'm going to calculate x at minus 2, at minus 1, at 0, at 1, at 3 over 2, and at 2. If we put these values of x into the equation, we can calculate the value of y. For example, if x is minus 2, y is 1 plus minus 2 squared. 1 plus 4 is 5. Step 2, I want to plot these points on some axes. Here they are. This is the point where x is minus 2, y is equal to 5. And over here I have the point where x is 3 over 2 and y is 3 and a quarter. And then step 4, draw a smooth curve through these points. And here it is. This is the graph of y is equal to 1 plus x squared. Now, not every curve that you can draw is the graph of a function. On the left, I have the graph of the function we've just done, and on the right, I have a circle. Note that a vertical line intersects the graph of the function we've just done at 1 point, but the line that I've drawn intersects the circle at 2 points. Because a function can only have one value of f of x for each x in the domain, this means that a vertical line can intersect a graph of a function at the most 1 point. That tells us that a circle cannot be the graph of a function because some lines, such as the one I've drawn here, intersect the circle at 2 points. If a is in the domain of the function, then the vertical line x is equal to a will intersect the graph of the function only at the point a f of a. This is called the vertical line test. Piecewise defined functions. We can define a function using different formulae on different parts of the domain. For example, the function absolute value of x. This is defined to be equal to x if x is greater than or equal to 0, or minus x if x is less than or equal to 0. Or we might go a little bit more complicated. This function is defined on 3 different parts. It's minus x if x is strictly less than 0, x squared if x is between 0 and 1, or 1 if x is strictly greater than 1. Here's an example from your textbook. This is an example of the integer floor function. What this function does is it rounds down to the nearest integer. So if we start at, say, 2.4 and we go down until we get an integer, we get to 2. Or start at 1.9 and round downwards, we get to 1. If we start with an integer, for example, minus 2, we don't make any changes. The floor function of minus 2 is minus 2. If I started at, say, minus 0.3, and if I rounded downwards, if I go down until I get to an integer, then this is equal to minus 1. And the graph of this function is shown above. The filled in circles and the open circles show the value of the function at different points at different integers. There's another function called the ceiling function. You can think of this as the function which rounds up. So for example, if we put 1.5 into the ceiling function, it would round it up to 2. We'll need these later in the course. As we go through this course, you'll know that some examples I spend a lot of time on. Some of them I'm just picking a screenshot from your textbook and I'm going through it very, very quickly. If I go through it very, very quickly, that's because I'm leaving that for you to read the details in your textbook. Increasing and decreasing functions. Let I be an interval, some type of interval, finite or infinite. And let f from I to r be a function. The function f is called increasing on I if this rule is satisfied. F of x1 is strictly less than f of x2 for all x1 and x2 in I, which satisfy that x1 is strictly less than x2. And decreasing if we have almost exactly the same thing. The only change here is less than changes to greater than. Still, x1 is less than x2, but now we insist that f of x1 is strictly greater than f of x2. So for example, this is an increasing function. As we go from the left to the right, the function is always going upwards. And this is a decreasing function. As we go from the left to the right, the function is always going downwards. For example, if I picked x1 just here, and I picked x2 just here, the value of the function at x1 is bigger or greater than the value of the function at x2. This function is not increasing because it's not always going upwards, and it's not decreasing because it's not always going downwards. We can classify functions as some functions as even or odd. Let me first remind you that the numbers 2, 4, 6, 8, and 10 are the even numbers, and the numbers 1, 3, 5, 7, 9, etc. are the odd numbers. A function f is called an even function if this rule is satisfied. F of minus x is always the same as f of x. And it's an odd function if we have a slightly different rule always satisfied. F of minus x is minus f of x. For example, x squared is an even function because, and this is how we show it, we start with f of minus x, that's minus x squared, which is the same as x squared, which is the same as f of x. Graphs of even functions always have the property that we could put a mirror on the y-axis. Then the left side of the graph is a mirror image of the right side of the graph. We always have left-right symmetry about the y-axis. X cubed is an odd function. Why? Again, we're going to start with f of minus x. That's minus x cubed, which is minus x cubed, or minus f of x. Odd functions, or graphs of odd functions, have the property that we could rotate the graph 180 degrees around the origin, around the point 0, 0, and the graph would be exactly the same. What about this one? Is x squared plus 1 even, odd, or neither? It's possible that it's not even and it's not odd. So to answer that, I'm going to start with f of minus x again. Minus x squared plus 1, which is the same as x squared plus 1, which is the same as f of x. This function is an even function. What about x plus 1? Is that even, odd, or neither? Now, this time, instead of doing it for all x, I'm just going to test it for one number. I'm just going to test it at 2 and at minus 2. If I calculate g at minus 2, I get minus 1. If I calculate g at 2, I get 3. But these numbers are not connected. We don't have that g of minus 2 is g of 2, so it's not even. And we don't have that g of minus 2 is minus g of 2, so it's not odd. This function is neither even nor odd. If you need to prove that a function is even or prove that it's odd, you have to prove that the rule is satisfied for all values of x. If you just want to prove that it's not even or not odd, then you just need to test one number. We just need to find at least one point where the rule doesn't work. The opposite of always being true is being false at least one point. And then for the end of the first half of this lecture, I want to run through some common types of graphs. Linear functions are the functions whose graphs are straight lines. They're functions of the form mx plus b for numbers m and b. I'm deliberately going to be very, very quick in this section. Power functions are functions of the form x to the power of a for some real number a. So for example, y is equal to x. That's a power function of a equal to 1. Or y is equal to x squared. Y is equal to x cubed. Y is equal to x to the power 4, etc. But we don't have to have positive values of a. We might also have negative values of a. X to the power minus 1 is the same as 1 divided by x. Or I might have a fraction, for example, a is equal to a half. X to the power of a half is the same as the square root of x. X to the power of a cube of 1/3 is the same as the cubed root of x. X to the power of 3/2 looks like that, and x to the power of 2/3 looks like this. Polynomials are functions like this. Some number a n, x to the power n, plus some number a n minus 1, x to the power n minus 1, etc., plus a2 x squared plus a1x plus a0. The natural domain of a polynomial is always the whole real line, always all of the real numbers between minus infinity and infinity. And as long as n is strictly greater than 0 and an is not 0, the number n is called the degree of the polynomial. If we do polynomial divided by polynomial, then we get a type of function called a rational function. For example, 2x cubed minus 3 is a polynomial, 7x plus 4 is a polynomial. So 2x cubed minus 3 divided by 7x plus 4 is a rational function. A to the power of x, where a is a real number, a is strictly greater than 0, and a is not equal to 1, is an exponential function. The natural domain of an exponential function is also the whole real line. The opposite or the inverse of an exponential function is a logarithmic function. We can write y is equal to log base a of x if and only if a is equal to a to the power y. And again, a needs to be a real number, a needs to be strictly greater than 0, and a must be not equal to 1. And that brings me to the end of the first half of today's class. Now we're going to take a break until 2 o'clock. I'm sorry, until 3 o'clock, I should have said. Our next topic is the topic of combining functions, shifting and scaling graphs. First, let's talk about sums, differences, products, and quotients of functions. Let's suppose we've got two functions, a function f with domain d of f, and a function g with domain d of g. Then we can define four new functions. We can do f plus g, f minus g, f multiplied by g, or f over g. And we define these in the obvious ways. But what are the domains of these functions? The domain of the first tree, we need f and g to both be defined. So we need the domain of f intersection the domain of g. You can imagine if f is defined here and if g is defined here, then we only want the part where both f and g are defined. For f over g, we need one more condition. Again, we want the intersection between the domain of f and the domain of g. But we also need to make sure that g is not equal to 0. So for example, let's suppose f is the function square root of x. That's defined on the non-negative real numbers. And let's suppose g is the function square root of 1 minus x. That's defined on the the closed interval between a minus infinity and 1. Find f plus g, f minus g, fg, f over g, and g over f, and find the domains of these 5 functions. Okay, I've written the information that we needed in the yellow box at the top. First, let's talk about f plus g. The formula is easy, just square root of x plus the square root of 1 minus x. The domain is going to be the intersection between the two domains. The intersection between the interval from 0 to infinity and the interval between minus infinity to 1. What are the numbers which are in both of these domains? It's the numbers between 0 and 1. F minus g and fg are the same, they have the same domain, and we can easily write down the formulae for these functions. What about f divided by g? Or g divided by f? The formulae are easy, but what about the domains? We need to take care that we're not dividing by 0. F over g can't be defined when x is equal to 1. So we need the half open interval between 0 and 1. And g over f cannot be defined or is not defined when x is equal to 0. So another half open interval, but this time it's open at 0 and closed at 1. F circle g, that means f of g of x. And that's the composite of f and g. We read this as f composed with g. So it means we take our number x. First we calculate g of x, and then we calculate f of g of x. What's the domain of this? The domain is all of the numbers x, which are in the domain of g, but with the extra condition that the number g of x is in the domain of f. A graphic from your textbook. Think of this as two machines. First, we put x into the first machine to get a number g of x, and then we put that into the second machine to get a new number f of g of x. Or we might think of it something like this. We start at a point x, we use the arrow called the function g to get to a new point g of x, and then we do another function, another arrow, to get to the point f of g of x. Or we could do that in one go. Using the red arrow, we can go all of the way from x to f of g of x. For example, if f of x is the square root of x and g of x is x plus 1, find f composed with g, g composed with f composed with f, and g composed with g, and find the domains of these four functions. Note that the domain of f is the non-negative real numbers, the closed interval between 0 and infinity, and the domain of g is all of the real numbers. F composed of g, that's do g first and then do f of the result. So first we take x and we add on 1 to get x plus 1, and then we take the square root of that number. We can put any real number into g, but we need to obtain a positive number before we can take the square root. So the numbers that we can put into f composed of g are numbers between -1 and infinity. G composed with f. We know which numbers we can put into f. We can put the non-negative real numbers in, and then after that, g is easy. G will take any number. So the domain is the non-negative real numbers. F composed of f, square root of the square root of x, or the fourth root of x. The domain is the non-negative real numbers, and g composed of g. G will take any real number, so the domain must be the whole of the real line. Do g, we add on 1. Do another g, we add on another 1. G composed of g is x plus 2. Our next idea is the idea of shifting. Let's suppose we have some function, and I want to shift the graph in different ways. So perhaps I want to shift the graph up, or maybe I want to take my original graph and I want to shift it downwards. Maybe I take my graph and I shift it to the left, or maybe I take my graph and I shift it to the right. How can we do this? Shifting up is easy. We can just add on a number. F of x plus k shifts the graph up k units. That's if k is a positive number. If k is a negative number, then it would go the opposite direction. It would go downwards. We can shift it to the left by putting the plus k inside the brackets, looking at f of x plus k, close bracket. This would take our graph and shift it to the left by k units, or if k is a negative number, it would shift to the right, the opposite direction. Let's look at some examples. Again, let's take this function. This is the graph of y is equal to f of x for some function f. If I want to shift it upwards, I just add a number on. This is the graph of y is equal to f of x plus 20. I'm taking my graph and I'm going up 20. Go back to the original one. Let's say I want to go down 20. That's easy, just subtract 20 from it. This is the graph y is equal to f of x minus 20. Back up. Let's say I want to take this graph and I want to shift it to the left by 1 unit. We do that by doing plus 1 inside the bracket. This is y is equal to f of open brackets x plus 1 closed bracket. And to shift to the right, we do the same thing, but instead of plus 1, we do minus 1. This is the graph y is equal to f of x minus 1. For example, shift the graph y is equal to the absolute value of x by 2 units to the right and then 1 unit up. Okay, let's go to the right first of all. If we want to go to the right, we replace x by x minus 2. And then I want to go up 1. That's the easy bit, just do plus 1 on the end. The answer to this question is y is equal to the absolute value of x minus 2 plus 1. Scaling and reflecting. This time I'll show you the formulae first and then I'll show you the graphs. Here I'm assuming that c is greater than 1. If we take y is equal to f of x and we multiply it by c, then we're going to be stretching vertically. Or if we multiply by 1 divided by c, then we're squashing it vertically. If we put the c inside the bracket, so if we're looking at f of cx, just like with shifting, if we put the term inside the bracket, then it does the opposite effect of what we would expect from putting it outside. F of cx squashes horizontally, and f of x over c stretches horizontally. If c is equal to minus 1, then we get a reflection. Replacing y is equal to f of x by y is equal to minus f of x, this reflects it vertically. We can imagine that we put a mirror on the x-axis and we flip the top to the bottom and the bottom to the top. If instead we put the minus sign inside the brackets, then we're reflecting horizontally. We can imagine that we put a mirror on the y-axis. So for example, let's go back to this function. If I multiply this function by c, then I'm stretching it horizontally. The points which cross the x-axis are going to stay the same, but everything else is going to be stretched upwards or stretched downwards. If we look at y is equal to 1 over c, squashing it vertically. Y is equal to f of cx, that's a horizontal squash. And y is equal to f of x over c is a horizontal stretch. This is the original graph. Now I want to be reflecting this. So imagine we put a mirror on the x-axis and we reflect the top to the bottom and the bottom to the top, like this. This new function is y is equal to minus f of x. And if instead we put the mirror on the y-axis and we reflected left to right and right to left, we would get f of minus x. There's one more example in your textbook, which I leave for you to read. Please read example 5 when you have a free moment. Instead of doing example 5, I want to move straight on to talking about the trigonometric functions. But before we can talk about the trigonometric functions, we need to talk about angles. There's 2 ways to measure angles. We can measure angles using degrees or using radians. How do we do radians? Imagine that we have a circle of radius 1. And then let's suppose we want to measure the angle between these 2 rays. What we do if we're using radians is we measure the angle around we measure the distance around the outside of the circle of radius 1. And that distance is the angle in radians. So for example, if I had half a circle, a semicircle, we know that the angle I've marked here is 180 degrees. And the angle around a semicircle of radius 1 is pi. So 180 degrees is the same as pi radians. If I divide both sides by pi, 1 radian is the same as 180 over pi degrees. Or if I take the first line and I divide both sides by 180, 1 degree is the same as pi over 180 radians. Here are some common angles. 45 degrees is the same as pi over 4. 60 degrees is the same as pi over 3. And 90 degrees is the same as pi over 2. Now, note, if we use degrees, we have to write a little circle to say we're using degrees. When we use radians, we don't use any notation. We just write a number. Some more pictures from your textbook. If we are starting at the x-axis and we're measuring an anti-clockwise angle, like in the left picture, then we say the angle is a positive angle. If instead we're going clockwise, like in the right-hand picture, then we say that we have a negative angle. So for example, these are the angles 9 pi over 4, 3 pi. 2 pi is the same as 360 degrees, so it's 360 degrees plus another pi, or plus another 180 degrees, minus 3 pi over 4, and minus 5 pi over 2. In calculus, we use radians. If you see an angle in this course, it will almost always be in radians. Why? Because calculus doesn't work with degrees. I'll explain why in a future lecture. Let's talk about the trigonometric functions: sine, cosine, tangent, secant, cosecant, and cotangent. Imagine now we have a circle of radius r. We have a point on the circle, and we've measured the x and y coordinates of the point. And let theta be the angle between the x-axis and the green ray. The function sine of theta is defined to be y divided by r, and the function cosine of theta, or cos theta, is x over r. After we've got those two, we can combine them together to get the other four. Tan means sine divided by cos. Sec means 1 divided by cos. Cosec, and there's two common ways to write cosec. If you want to use 3 letters so it matches the other one, you can write CSC. If you want something that's easier to pronounce, you could use 5 letters and write COSEC. Completely up to you which one you use. That means 1 divided by sine, and cotangent, or COT, means cos divided by sine. That's almost exactly 1 divided by tan. Let me just note that tan and sec are only defined as long as cos theta is not 0, because we can't divide by 0. And cosec and cotan are only defined as long as sine theta is not equal to 0. Let's look at some common angles. This is a right angle triangle. 2 sides are equal to 1, and using Pythagoras, the other side must be the square root of 2. The angles are pi over 4, that's 45 degrees, pi over 4, and pi over 2, which is 90 degrees. From just looking at this triangle, we can calculate sine and cos of pi over 4. For sine, I'm using this angle, say, using the bottom angle. 1 divided by root 2. For cos, again using the bottom angle, we do this 1 divided by root 2. And then after you've got those two, we can get the other 4 easily. Tan is sine divided by cos, so 1. Sec is 1 divided by cos. Cosec is 1 divided by sine. And cotan is cos divided by sine. Another common one, let's suppose we start with an equilateral triangle of side 2. So the angles inside this must all be 60 degrees or pi over 3. And then let's suppose we cut this in half. Then we get a triangle with sides 2, 1, and by Pythagoras, the other side must be the square root of 3. Sine 60 degrees, or sine pi over 3, must be root 3 divided by 2. Cos of pi over 3, or cos of 60 degrees, is 1 divided by 2. And then after you've got those two, you can get the other 4 easily. Here are some more common results from your textbook. Try to learn as many of these as you can. Periodicity. A function f of x is called periodic if we can find a positive number p such that f of x plus p is the same as f of x. There's going to be infinitely many possible p if p exists. The smallest such positive p is called the period of f. So for example, the period of tan x is pi because tan of x plus pi is the same as tan x. This is the smallest positive p which works here. The period of sine x is 2 pi because sine of x plus 2 pi is equal to sine of x, and we can't put a smaller number in. The graphs of the functions look like this. Again, this is taken from your textbook. We can see here the period of sine, say, is 2 pi. We have this shape, which then repeats again and again. Or, for example, tan, we have the shape in the middle between minus pi over 2 and pi over 2, and then this shape repeats it again and again and again. So the period here is pi. These trigonometric identities, I'm assuming that you know from high school. Because of the way they're defined, using a triangle or circle, cos theta is sine of pi over 2 minus theta. This one I think everybody remembers. Cos squared plus sine squared is equal to 1. If I take this red identity and I divide by either cos squared or by sine squared, then I get the next two. Another two, which I think everybody remembers from high school, cos of a plus b is cos a cos b minus sine a sine b, and sine of a plus b is sine a cos b plus cos a sine b. We'll need them later in the course. Write a and equal to b equal to theta, and we get the next two. And finally, if I take the two which are now in red, and I combine them together, then I can get the bottom two on this slide. An identity which is not as well known is the law of cosines. Suppose we have a triangle like this, which is not typically a right angle triangle. How are A, B, C, and theta related? Let's put this on an XY axis, and I want to put the origin, the point 0, 0, at the corner where I'm measuring my angle, and I want to put the side B along the x-axis. Then just looking at the line of length A and the angle, we can see that the orange point has coordinates a cos theta, a sine theta. I need another triangle, which I'm drawing in green now. This triangle, we know its height and we know the length of its base. The height must be a sine theta because the orange point has y coordinate a sine theta. And the base of this triangle must be b minus a cos theta. Why? Because this must be b and this must be a cos theta. So b minus a cos theta. So just looking at the green triangle now, using Pythagoras, c squared must be b minus a cos theta squared plus a sine theta squared. I'm going to multiply this out and simplify it. B minus a cos theta squared is b squared minus 2a cos theta plus a squared cos squared theta, and then we got plus a squared sine squared theta. There's a cos squared plus a sine squared here. Everybody remembers, if I teach this in a classroom, everybody immediately calls out, that's equal to 1. So we just end up with a squared plus b squared minus 2a cos theta. And that's the identity I wanted. That identity is called the law of cosines. For example, in the special case where we do have a right angle triangle, where we have theta is pi over 2 or theta is 90 degrees, then because cos pi over 2 is just 0, this just reduces to Pythagoras. C squared is equal to a squared plus b squared. I need two special trigonometric identities. This is the last idea for today's lesson. Let's suppose we have a circle of radius 1, and we have a point P on the circle, somewhere on the circle, anywhere on the circle. And the angle between this green line and the x-axis I want to call theta. Now, because of the way that radians work, and because we have a circle of radius 1, this distance in red is also theta. That's what radians mean. Radians mean the distance around the outside of a circle of radius 1. I want a triangle here. This green triangle has base cos theta and height sine theta. Let's zoom in a little bit. And there's one more triangle I need. This orange triangle, the base of this orange triangle is 1 minus cos theta because the circle is radius 1 and we've already got cos theta, so this must be 1 minus cos theta. And the other side, I don't know, haven't calculated yet, so on the other side I'm just going to call h. Right, let's remove everything in this picture that we don't need. The line of distance h is a straight line. The red curve is not a straight line. So the length of the red curve must be longer than the straight line. So from this picture, I must have that h is smaller than theta. And because they're both positive numbers, h squared must be smaller than theta squared. Using Pythagoras, I know h squared, H squared is just 1 minus cos theta squared plus sine squared. Everything here is positive. It's positive number plus positive number is smaller than positive number. We can split up the left-hand side and it's still true. 1 minus cos theta squared must be smaller than theta squared, and sine squared theta must also be smaller than theta squared. Take the square roots. We must have that sine theta is between minus the absolute value of theta and theta. And 1 minus cos theta must also be between minus the absolute value of theta and the absolute value of theta. We're going to need these two special inequalities next week when we start talking about limits. But for now, that's the end of today's lecture. Next week, we move on to chapter 2. I'm going to talk about rates of change and tangents to curve, limits of a function and limit laws, and the precise definition of a limit. Are there any questions? Okay, let me switch to my Chrome tab. There were questions about where to find the slides, about the course ID, and where to find the recordings of the lectures. First item in course content is this course calendar. Click on any of these pictures on Fridays and you will load a PDF of that week's slides. In the left menu, click on homework. Go down to the 4th entry. You will see that the course ID is course 46757, but you probably don't need this. If you click any of these 3 links at the top, then you will automatically go to the right course in MyLab. If you're asked for the course ID, then it sounds like something's going wrong. Where can we find the recordings? Click on Colab, open bracket, classroom. Find the hamburger icon to the left of sessions. Click on that and it opens a sub menu, and one of these options is recordings. At the moment it's empty. It says no recordings found in the last 30 days. There will be one in 10-15 minutes after the system has updated it. There are 4 homeworks available at the moment out of 12. So I've written 4 and I haven't written the last 8 yet. I can't tell you what's enough because it's going to be different for different people. For some people, yes, some people will pick the material up quickly and they'll be able to answer the exam questions easily. Other people will need to do lots and lots of work. It's up to you. We haven't written the exam yet, so I can't answer that, but we will definitely need the material in today's lesson in future lectures. I finished with these 2 special inequalities. I know we're going to use these next week. We're going to be using intervals all the way through the term. We're going to be using real numbers. We're going to be using radians and trigonometric functions through the course. So these ideas will come up. Whether or not there's actually an exam question from chapter 1, we haven't decided yet. The homework deadline will be 1 day before the final exam. At the moment, I've set it to, I think, the 23rd of May, something like that. And then after I learn the final exam date, I'll change it as necessary.